Okay, let's start. So good news is that I think we can finish special relativity today, and then we can really move on to the main subject of this course. And actually the stage has been set for the most important thing, which is actually the definition of a Lorentz transformation in general. So we'll introduce this notation first, x mu, where mu goes over 0, 1, 2 and 3, and this is equal to Ct and the 3 vector x. So we combine time and space into one 4 vector. You probably used this before. There's a history in this use of 0. Old papers often used 4. I think even Einstein might have used 4 for time as the 4th dimension. But then people realize that, well, it's not on the same footing as 1, 2 and 3. Time is actually different from space. And it comes in the invariant quantity with a negative sign. That's somehow responsible for all the interesting things. So eventually it became a standard convention to call it 0. So the question then is, what is the most general transformation, linear transformation between x and a new frame coordinate x prime, which we are now going to write as lambda upper nu lower nu x nu. So lambda is a 4 by 4 matrix, and we are just going to assume this in the same way that we assumed rotations send xi to oij xj. It's a similar concept. If people are having a hard time reading anything here, I will put on the lights. It's more important for you to see than for the video. It's the lights are not very good for the video. Yeah? You can't see. Oh, then definitely we'll have some lights at least. Either this or what are our other options. Does this help? This might help. Okay, good. Great. Okay. So we just want lambda to satisfy whatever conditions. Lambda such that minus c squared dt squared, the same thing, plus dx squared is invariant. So for this, we'll also write this in a convenient form. This quantity minus c squared dt squared plus dx squared, we'll introduce a matrix eta mu nu and then multiply by dx mu and dx nu, and I claim this is the same as that. Okay, following the summation convention that the repeated index mu is summed over and repeated index nu is summed over. And but of course this can only be true for a definite matrix, and the matrix eta mu nu, which plays a fundamental role in special relativity, is that. So it's a diagonal matrix with elements minus 1, 1, 1, 1, and it's a very obvious exercise that if I carry out this sum, the only terms which can contribute are when mu and nu are both 0, then I get a minus sign, minus 1, and I get this term, because dx0 is c dt, so dx0 squared is c squared dt squared, and then when mu and nu are 1, 2 and 3 both equal and equal to 1, 2 and 3 respectively, I get each of the terms in this. So it just summarizes that quantity into a matrix, and as I said, this matrix is very fundamental. It's called the Minkowski metric. Why it's called a metric will slowly become clearer. We'll be using this word throughout the course. Right now, just think of it as the matrix which takes an arbitrary bilinear in dx's, the 4 vectors, and produces exactly this thing, which is the quantity which we want to keep invariant under Lorentz transformations. It is the invariance of this which defines Lorentz transformations. Now, in a way, we are being more general than we were earlier, because earlier we asked for invariance of only minus c squared dt squared plus dx spatial component, in one direction, just x, not y and z. Now we are asking a more general question: what keeps invariant the whole thing? And we are now going to use the word Lorentz transformation for anything which keeps invariant this whole expression. Okay. Now let's see how to solve this requirement that lambda is such that this is invariant. Well, all we have to do is write out eta mu nu dx prime nu and require it to be the same as eta mu nu dx nu. This is the precise statement of invariance. Okay, and eta is just always the same. We are not doing anything to eta, but we are going to change x prime by this equation. Equivalently dx prime. You can just take the infinitesimal version of this and plug it into this side. Okay. Now if you do that and don't make any mistakes, so I'll just use my notes. This quantity comes out to be eta mu nu, then lambda mu alpha, lambda mu beta, dx alpha, dx beta. So here I'm a bit unsure how much you are used to this business of repeated Greek indices, because this is going to be the look of all equations till the end of the course. Okay, they are all going to have lots of indices, mu, nu, alpha, beta, gamma, delta and so on. And whenever we see two of them equal, we are going to sum over them over 0, 1, 2 and 3. It's just understood. Okay. But there's one new thing here, which is that lambda has one index upstairs and one downstairs. The reason for that will be clear in a little while, before the end of this class. Okay, and the rule is to contract only indices downstairs with indices upstairs. So if alpha is repeated down and up, then we are summing. In fact, you will never find alpha to be repeated when it's both down. So you will not find any formula like that. So you never have to ask about summing over an index alpha when in two quantities when it's down in both. And we'll see why also in a few minutes. So it's just notation, it's just the notation I want you to be comfortable with. So we want this to be equal to that. Okay. One thing which you also should get experience with if you don't have it already, these are called dummy indices, because what are the free indices of this whole expression? There aren't any. Mu has been summed, nu has been summed, both sides. Okay. So this expression, I could have used alpha and beta in both places and nothing would really change. It's just a different name for the index which is being summed. Okay. So now to compare this with this, I need to extract the matrix multiplying dx on both sides. But for that, I'll have to first rename mu and nu here as alpha and beta. Then this is the same as that. So this must be the same as that. And so I get the equation eta mu nu lambda mu alpha lambda mu beta is eta for beta. This is the defining equation of lambda. Eta has been given to you. And where did eta come from? It's not something mysterious. It's just a matrix which encapsulates this quantity, which is the quantity which has to be invariant so that the speed of light can be the same in all frames. So eta is given, and any lambda which satisfies this, any matrices lambda which satisfy this are going to be called Lorentz transformations, and we can anticipate, since we have already done the calculation, that the matrix lambda which we wrote once with cosh and sinh of theta, that one will work. But we don't know exactly how many will work. It's a 4x4 matrix now. So all linear transformations between any x, y, z and t are all going to be encapsulated here. Those which satisfy this equation will be called Lorentz transformations, and they are the set of invariances of the theory of special relativity. Anything we do should be invariant under all of those transformations. If we don't do it, then light will not have the same speed in all frames and will not have special relativity. It's as simple as that. Okay. Now it's convenient to rewrite this equation in terms of a matrix product. All of these are 4x4 matrices. But the product is not written in a form where I have a straightforward product of matrices. You know this from yesterday. When I multiply two matrices, it's the second index of the first matrix and the first index of the second matrix. I'm sure you know this. M, I, J, N, J, K is equal to A, I, K. This is the standard rule of matrix multiplication, where the common index J is summed over, and it's the second index of this matrix and the first one of this matrix. I do hope you know it. No, nobody's looking very happy. Okay. And this equation can also be written as Mn equals A without any indices. Because now we can put the indices Ik on both, and then we can expand out Mn by the matrix product rule. So can we do something similar here? Does anyone have suggestions? How do we rewrite this in a form of a matrix product?
Lambda is fine as it is.
Huh?
The second lambda is fine as it is.
Second lambda is not fine as it is actually. The reason is the final indices on the left side have to be first alpha and then beta. For this to be a matrix product, we first have to have a matrix which starts with alpha.
Transposing?
Thank you. Transpose. So we'll first copy this one as lambda transpose alpha mu. The transpose of a matrix is just the matrix whose rows and columns are interchanged. So, and I always preserve the rule that if this was down, it stays down. If this is up, it stays up. But now this goes to the front and this goes to the back. So this is the same as this. Next, I write eta nu. I'm just copying it. And finally, I write lambda nu beta. Now does it look like a matrix product? Because the common indices are these two and those two. So this whole thing, now I can write that equation abstractly as lambda transpose eta lambda equals eta, which is a much nicer equation, easier to remember. And it's the characterization of Lorentz transformations. It is those transformations whose matrix lambda satisfies lambda transpose eta lambda equals eta. Now, does this remind you of any equation?
Looks very much like the identity matrix.
Very good. It looks like the identity matrix. Thank you. That is exactly what I was going to say. But for one thing, it is the identity matrix in this part, but this -1 spoils everything. And it's not just a mathematical trick. The -1 is because it's time, and time and space do have a relative sign, as you can see in this equation. So it's similar but not the same. But there was a similar equation yesterday. What was it? Rotations, where we had O transpose O equals 1. There was no eta in it. But now we see that this actually just generalizes rotations. And actually the whole story of special relativity is that it generalizes rotations to include boosts. And this is the exact formula which does that. And now we can try to look for some solutions which are familiar to us. Before that, I'll introduce some more notation, and it's really important.
Sir, I have a doubt.
Yes, please.
When you transpose lambda, how does the indices go?
First index becomes second, second index becomes first. Up doesn't go down. This one I transpose. This was the first index. That's why you see, to start with, I wrote it this way. I didn't put nu directly under mu because I wanted it to be clear which is the first index and which is the second index. Since actually many of you, except maybe the IPhD students, have taken a course in linear algebra, this is just a endomorphism, if you like. This is an operator which acts on a vector to give another vector in the same vector space. And when we write all that out in components, we have to contract the second index of it with the vector, leaving the first index which labels the new vector. It's just the index version of something that you have learnt in linear algebra. It's just a map from one vector space to itself. Okay, good. So now there's one more thing to be done. So one thing I would like to emphasize, we started by putting the index up on mu. All the other indices followed from that rule. Because I've made a rule that we can't sum over indices which are both up or both down. So for this to work, if mu is up, nu has to be down, this nu has to be up. It's a convention that coordinates always are written with the indices up. All other conventions should follow from that. Okay, so once we have chosen that convention. And now we notice that eta is a matrix with both its indices down. Okay, so if we want to consider the inverse matrix to this, we'll have to change the location of its indices in such a way that the statement matrix times matrix inverse is 1 makes sense, and we'll do it now. Of course, you can see by inspection what is the inverse of this matrix? Itself. You just square it, you get 1. But we are going to still give it a different name, and for that we'll simply write eta upper mu, eta inverse upper mu nu is the same matrix. Okay. In future, we won't specify whether we are referring to eta or the inverse because it's literally the same. But the point is that by doing this, actually we don't write inverses. We just write it as eta upper mu nu. Now you see the obvious equation that if eta mu nu is contracted with eta nu lambda, I get delta mu lambda. What is this equation? First of all, this is the identity matrix. Kronecker delta defines for me the identity matrix. And the identity matrix has one index up, one index down, and it doesn't need any Minkowski metric or any other thing to define it. This is simply 1 when mu and lambda are both 0 or both 1 or both 2 or both 3. It never is -1. This thing is always 1 or 0. And the statement that one matrix times another with matrix multiplication is the identity. That's the statement that one of them is the inverse of the other. So eta inverse has been written down. Same matrix but just written with indices up. Okay, all of this will become much clearer in another 5-10 minutes, so just bear with me till I write down a few formulae, and then we'll explain the meaning of all of them. Now what we want to do is to solve this equation, and it's not so easy to write an explicit solution. This will lead you into the direction of group theory, Ollie algebra theory, and it's a little too complicated for our purpose. However, let's write a couple of solutions and then you'll realize that all solutions look like products of this. So first of all, I can take lambda, so I'm trying to write lambda mu nu, which solves that boxed equation down there. And as an example, this is an equation which does the job. This is a solution which does the job. So what is this? First of all, you must recognize it, I'm sure. See, the indices mu and nu run over 0 to 3. So this is, if you like, the CT, the X, the Y and the Z component of the rows, and these are the columns labeled also by CT, X, Y and Z. The one should be here. Yeah, thank you. Yeah, why should we? Yeah, 1 should be there, that is correct. So you see that this acts trivially on y and z. Just imagine it acting on the vector CT, x, y, z. This acts trivially on y and z, and this acts on t and x. How? As a Lorentz transformation, the one we derived in the very first lecture. Okay, so that's good. This is a special case. Okay, let me write for you another special case. Instead of this, I'll write here 0, 1, 0, 0, and then I will write minus sine hyperbolic theta, cos theta, sorry, this was not good. Here's another solution. What does this do? Everybody, it should be clear to everybody what this is.
Mixes T and Y.
It mixes T and Y. It doesn't act on X because of this 1 over here. And it mixes T and Y exactly as earlier we had mixed T and X. And of course we expect it to be there, right? Because this is a Lorentz transform, a Lorentz boost in the y direction. If it was possible to do in the x direction, it's also possible to do in the y direction. As an exercise, please write down the analogous matrix for a Lorentz boost in the z direction. Okay, and to convince yourself that it is what I say, you have to multiply this with the vector c dt, dx, dy and dz and do matrix multiplication. Once you do that, you will get the answer I'm claiming. Okay, so we see that, so summary, there are at least three Lorentz boosts included in this relation, and they are the boosts in the, so boosts always are between time and one space direction. Okay, so there are at least three of those. Now let's write a lambda which is not like any of those. Another example, lambda mu nu is 1, 0, 0, 0 cos alpha sine minus sine alpha sine alpha cos alpha. What is this? This is just a rotation. This is a familiar rotation matrix. It's a 2 by 2 matrix embedded inside this 4 by 4 matrix, and it rotates what and what? X and Y. And how do we know it's a rotation matrix and not a boost matrix?
T is uninvolved.
T is not involved. There's a 1, so T doesn't change. Secondly, these are trigonometric and not hyperbolic functions. So alpha is really an angle. When you see cos of something, that thing has to be an angle. When you see cos of something, that thing cannot be an angle. That's a big difference. And also, this is antisymmetric, while these are symmetric. The boosts are symmetric and the rotations are antisymmetric matrices. Just a fact of life. You can also verify that the determinant of this is 1 because cos squared plus sine squared is 1. Here the determinant is cos squared minus sin squared, but that's also 1. So the determinants are 1. Good. Now, so obviously there are two more like this between. So this is, so therefore we have three rotations. X, Y, Y, Z and X, Z. And once you know these six, the claim, which I won't prove here, and those who are so inclined can always look it up, the claim is that these six matrices generate a group which is the full Lorentz group. So anything which satisfies my boxed equation lambda transpose eta lambda equals eta must be some product of those boosts and these rotations. Now they don't commute, so I can't tell you in which order I have to take the product. So in general, the general expression for a most general Lorentz transformation can be very, very complicated, and we don't have to care. Why do we not have to care? Because we want our laws of physics to be invariant under Lorentz transformation, and if they are invariant under every one of these and every one of these, then they will be invariant under any product of them, no matter how complicated. So we don't have to spend all our time sitting and trying to find out what that product is. If somebody says, I want a Lorentz transformation which actually rotates in a plane which is slanted with respect to x, y and z, and then also a boost in some northeast direction and not really x or y or z but some combination, you may spend a lot of time trying to find out what it is. But if the laws of physics are already invariant under these basic ones, then they are invariant under all. So this is like a basis. Now group doesn't have a basis in that sense, it's an algebra which has a basis, but again that's a long story. Let's just say that this defines the group O3, 1, which is a generalization of the rotation group O3. Now there are some subtleties because these are all continuous transformations. You see that if theta is 0 or alpha is 0, I get back the identity. So these are what are called continuously connected to the identity. That means I can perform this boost or rotation by a very small amount, and as that small amount goes to 0, I have no boost or no rotation. But there's an interesting solution of this equation where the whole lambda is the matrix minus 1, minus 1, minus 1, minus 1, minus 1. It's a reflection of all the directions. That clearly solves this equation. But it's not continuously connected to the identity. So this is a subtlety. We have to break up in our minds which ones are continuously connected and which are not. If I need to use the not continuously connected ones, we'll discuss it again. It's just in case you had a question whether this group also includes such transformations which are not continuously connected to the identity, and it actually does. In fact, for the Lorentz group, it's pretty complicated. There are 2 or 3, there are a few different factors in the group, if you like. It breaks up into pieces, but we don't need to worry about that as long as we are going to be continuously connected. Yes?
So what do you mean by continuously connected?
I just explained. Continuously connected to the identity means a transformation which has a parameter such that when I take that parameter to 0, I get a identity or trivial transformation. So let's give an example with rotations. A rotation in the xy plane is continuously connected to the identity. Okay. However, reflection of x without doing anything to y and z is not continuously connected to identity, and hopefully you know what it is. It's called parity, and it's a very important discrete symmetry of physics. Actually, it's not always a symmetry, but it's a discrete operation in physics, and it's not continuously connected. It's mirror reflection. You can't reflect yourself in a mirror slightly. When you look at the image in a mirror, it's a totally different image from you with the left-right interchange, and that's it. There's no slight amount that you can do to get to that mirror image. If you went behind the mirror, you would not actually look like the mirror image, because the laws for that mirror image are the parity reversed laws.
It is discrete.
So it's a discrete symmetry. This is not relevant for what I'm going to do now. I just thought I'll mention it so that you can think about it. Okay, good. Okay, now let's stop focusing so much on light. Let's focus on some object that transforms at some speed, that moves at some speed v. Okay, I've told you before that there can be many different speeds in a problem. So now I'm going to consider an object that moves at a speed. Let me not even call it v, let me call it w, at a velocity w. Just not to confuse with v, which I use for going from one frame to another, and c, which is only the speed of light, which we never use for anything else. Yes?
Yesterday we talked about the active transform.
Yes.
Sort of, you told us that we have to change our function and sort of we are changing the
Yes.
result.
Yes.
So how do we come to know that we don't have to change the metric?
Good. Very good question. So this eta, we are going to come to the transformation of the metric in a few minutes. Just hang on, I will come to that. In fact, I am leading up to that. So if I have an object that moves at a velocity w, now that velocity can of course change with time. It's moving at some instant with the velocity w. So at some instant, then for that object, minus w squared dt squared plus dx squared. What can I say about the sign of this object? Is it positive or negative, or can it be 0?
Should be less than 0.
Should be less than 0. There's a vote for less than 0. What about other people? What would you vote for? Less than 0, greater than 0, equal to 0. What is it? I just want to know the sign, not the value. I don't know the value because I don't know w. This object is just 0 because it is the speed of the object is the velocity is w, but w is dx by dt. So this is 0 for that object, right? Now what is minus, so for this object, this is 0. What is this quantity for the same object? This is the quantity I want to know. Is it positive, negative, or 0 for the same object? It's negative. Okay, does everyone agree? And if so, why? It's negative because c is greater than in magnitude than w, because w is the velocity of a normal object, so that's less than c. And here we have minus c squared, so this is much less than that, but this is already 0, so this is less than 0. Okay, so we have actually learned something very interesting. Any object has any physical object, if you like. And again, I mentioned yesterday that we distinguish massless and massive objects. So I mean an object with a mass here. So maybe to be more physically precise, we should say any massive object. Massive, by the way, does not mean heavy. It just means it has a mass. Even neutrinos are massive. They just have a non-zero mass. Any massive object has this plus this less than 0, and this property is called time-like. The way to remember the word time-like is that between this term which has a negative sign and this which has a positive sign, which one is winning? The time part is winning, that's why it's negative. If the space part was winning, it would be positive, and if they are both equally balanced, then it would be 0. So when any vector has this property, it's called time-like. Okay, so any massive object has a time-like trajectory. It's just a statement we have concluded from what we already know. That's very interesting. Okay, what about light? So in fact, any massless object has minus c squared dt squared plus dx squared equals 0, including light. And for this property, there's also a name. The common name is null. It's also sometimes called light-like, but light-like is too many letters compared with null. And null is a nice word which occurs repeatedly in relativity, special and general. Okay, null generally means something is 0. Okay, so this quantity is null for light, and it's time-like for massive particles. And what about space-like? Can we get space-like? No particle can do that, but it's still good to write it down because we'll see that there's a generalization which actually can be useful. So minus c squared dt squared plus dx squared greater than 0 is called space-like. The reason is obvious. The space is winning over the time. Okay. The fact that no physical object can do this means that I cannot transmit signals when 2 points in space-time are separated by a space-like separation. It's quite a profound conclusion. I haven't assumed anything. These are just facts. These are just facts which follow from W less than C. Let's see what is this consequence. Here is the space-time diagram. Here is Ct, here is x. And here are 2 points, P1 and P2. At x1, Ct1 and x1, Ct2 and x2. And my question is, can a signal be transmitted across this? Well, yesterday we saw that on a space-time diagram, any curve that satisfies that its velocity is, any particle whose velocity is less than light, has to have a vector in this direction, and it gets faster and faster till it almost reaches the speed of light. There's no possible vector in that direction because the particle would travel faster than light. But we have managed to make this statement now look much more impressive. No signal can be transmitted over a space-like separation.
So, I mean, they cannot be causally connected.
Yes, exactly the same thing. That another way of saying it is not causally connected. You cannot influence what's happening there. So P1 and P2 are not causally connected. There's nothing very mysterious about it. Everything, as I said, follows from the fact that c is an upper bound of the speed. Because what is the meaning of causally connecting P1 with P2? P1 is an event, say a firework explosion which goes off on Earth at some time. P2 is some other firework or flash of light, but which goes off in some galaxy very far away from our Milky Way. At a later time. The problem is, even though this is a later time, this P2 is at a later time than P1, but it's still too soon for light to get there. If it's too soon for light to get there, it's also too soon for any matter to get there. Nothing can get there from here. So even though it's happening later than this event, there's no way we can get there and stop it, even in principle. That is the meaning of these two statements. Okay, we are basically seeing a lot of statements over and over again in different forms, which you need to absorb. But space-like separation is important, not because we can travel over it, but exactly because we can't. It puts these points out of causal contact. So if something bad was going to happen here and I knew about it here, there's still no way I could send any instruction, signal, radio message, wireless message to stop that thing from happening. Because to send that message, it would have to travel faster than light, and that's just not possible. Good. So that was time-like, space-like, and null. As you can guess, time-like is the most, in some sense, the most important when we are discussing particles. That's what all particles do except light. So for time-like, we have a very special, well, first let's give some names. I don't know if I used this name before, but we'll write ds squared is defined as minus c squared dt squared plus dx squared. This is for the trajectory of any particle, any object, light or otherwise. This is the quantity which is unchanged by Lorentz transformation. That's exactly what we first determined in the very first lecture, that this quantity is unchanged by Lorentz transformation. Okay, so this quantity has a name. It's called the invariant interval. Now, of course, it's actually the square of the invariant interval, so you could always write this as the actual interval. What is this interval? It is a quantity which is negative if the trajectory is time-like. So this square root, of course, becomes a little ugly because it will be imaginary. So that's why we prefer to write ds squared like this. Now, ds squared, even though it's written this way, it can be negative. ds is not supposed to be thought of as a real thing. ds squared is the thing, and it's just this quantity, just a name for this quantity. So we should get used to the fact that what we call ds squared can be positive, negative, or zero for relative, respectively, for space-like, time-like, and null trajectories. So this is what we call invariant interval. And if that is time-like, which means ds squared is negative, then we can define a quantity d tau, which is root of minus ds squared, and be divided by c. Note that s has the dimensions of length because both these terms have dimensions of length. So if I take, and s is, ds squared is negative for time-like. So minus ds squared is positive, so I can square root it and also divide it by c. Now the result has dimensions of time. Okay, so this is called proper time. So for any time-like trajectory, there is a proper time, and to write its proper correct definition, it is dt squared minus dx squared over c squared. It's simply the same thing, but with a common factor divided and also with a sign changed. Now, what is the physical meaning of proper time? This is the time seen by an observer by what is called a co-moving observer. So proper time, of course, is a Lorentz invariant. You can see the way I've constructed it, it's Lorentz invariant. I made it from the most famous thing, the invariant interval. Okay, so in any frame, proper time will be the same. But if I'm in a frame where I'm moving with the object, the particle, then dx is 0 because dx is how much the particle moves relative to the observer. But the observer is sitting with the particle, so it hasn't moved, so dx is 0. In that frame, the proper time is square root of dt squared, so it's just dt. Okay, so it's a more general quantity which is Lorentz invariant, which reduces to the time observed by an observer moving with the object. That is why it's called proper. Always means that. Okay, proper means with that object. That is what it's used for in relativity. Good. Okay. Now, in the next 10 minutes, we can now dispose of something that we've been talking about also last time, which is how physical quantities transform under Lorentz transformations. And we'll use whatever we did yesterday for rotations. Okay, one thing I forgot to say is that we use the notation, which might be a little confusing. We often use x as the argument of a function when it depends on all of them, all 4 coordinates. We don't write x mu, we just call it x. This is a notation. So you have to figure out whether x means the whole 4 vector or x just means the x direction. That depends on context. So now I'll say that a scalar under Lorentz transformations simply satisfies phi prime of x prime is phi of x, where x prime and x are related by a Lorentz transformation. It's the same logic as yesterday. In particular, if something satisfies this, then x prime might be related to x by a rotation, because rotations are part of Lorentz transformation. And in that case, it would be doing the job that a rotation scalar does, which we discussed yesterday. But if x prime is related to x by a boost, then also we can imagine something is a scalar. Okay, so a scalar is something which is just not influenced by boosting or rotating. So an example of a scalar in special relativity, but it's not a perfect example, is again the temperature. So the temperature is a field which has a value at every point of space-time, and if I rotate myself, obviously I'll see the same temperature. Now if I pass by that system at a velocity v, it's a little tricky to assume that we see the same temperature, because actually temperature is defined by black body spectrum, and moving very fast with respect to that will distort the spectrum and I might not see a black body at all. That is called redshift. So actually temperature is not a scalar, but we can just imagine it is a scalar, then it would satisfy this thing. There might be some quantities which satisfy this thing.
So,
Yeah.
I mean, are we defining something which will be fixed, and with respect to that we are defining scalar, or in terms of scalar we are defining the invariance? Like,
We are just, this equation again, it says that I have a function in one frame of reference which changes to a different function in a different frame of reference, such that the value of this function and this function at the same point is the same. That's always the
yeah, but
definition.
here
It's
you
what
are,
we did yesterday.
I mean, here temperature, as you said, so if it
Temperature,
is
you got temperature, let's forget that it changes black body spectrum. Let's assume that it doesn't depend on the boost. Then temperature of a point is the temperature of that point. It doesn't depend on putting any coordinates. It depends on you being there and putting a thermometer. Now somebody can come with one grid, somebody can come with some other grid, somebody can come with a moving grid. All of them should see the same answer. So that's this equation. It's the same meaning as yesterday, except that the transformation has been extended to cover rotations as well, to cover boosts as well. Yeah, I sometimes don't like talking about temperature, because really it's a very tricky story what happens to temperature in special relativity. You might want to actually ask ChatGPT the story. It's got a long history. Okay, so now we come to the next important thing, and that's going to be the vector. Now it's not possible anymore to have a 3-component vector because Lorentz transformations mix space and time. So it better have all 4 components. Okay, and so a vector can be written, for example, V mu, and I'll start with a vector which has mu upstairs because that's similar to the coordinate itself, which also had mu upstairs. And I'll propose the transformation law that V prime mu of x prime is lambda mu nu V mu of x. So the vector transforms exactly like the coordinate. Okay, but because I've chosen the index to be up and for V, I didn't know whether I should choose it up or down. So this has a name, it's called contravariant. And contravariant just means the index is up. Okay. So this is how a contravariant vector transforms, and it's reasonable to guess that there can be such quantities in special relativity, but more than that, there are quantities in physics like velocity, acceleration, force, vector potential, electric field, magnetic field. All are vectors under rotations. They must transform under Lorentz transformations because there's no way for them to be inert. If they were inert, they would be scalars. But they are not scalars under rotation, so they are not inert. So there must be something that there must be some way for them to transform, and that way must be determined by the Lorentz transformation matrix lambda, and it should be linear. So this is it basically. But now we come to a new thing which is not there in rotations. Suppose we define a new vector V mu, which is the Minkowski matrix eta mu nu contracted with V nu. I sum over nu. Now it has an index down, and now it's my job to find out how this transforms given how this transforms. They are not the same. And the fact that they are not the same is exactly why we have to keep track of the up and down. They transform differently, which I'll show you in a minute. Okay. First, let's see what is the effect of doing this. Can you guess what is the effect? This is a 4-component vector. Let's take V mu to be, just to not confuse with any coordinates, let's just call it ABCD. These are 4 numbers. So what is V mu? Minus A, BCD. Good. That's all. So it's a very trivial change, but this trivial change changes the way the vector transforms under Lorentz transformations. And let's do that calculation right now because it's extremely illuminating. So what we want is that V prime of mu we start with of x prime. So the covariant, this is called a covariant vector. Covariant means index down. Okay, contravariant index up, covariant index down. So this, by definition, it has to be eta mu nu. I first use the definition, this one. Eta never changes, so V prime mu is this times V prime upstairs. V nu prime upstairs. But this I know how it transforms from this equation. So this is lambda. Now I have to use new indices. Nu lambda V lambda x. Okay. So now I've got the answer in the unprimed frame, but in terms of V upper. But I want it in terms of V lower because that's what I started with. So what should I do now to get this back to the form? I can invert this relation. This relation has an inverse that V upper is eta nu mu V lower. Okay, both of these are true. There are exercises in my notes. By the way, the notes are now available on the shared on a shared folder, which I have mailed you all about. Good. So the last step, which I'll do and then I'll end, is that we get eta mu nu lambda nu lambda V eta lambda alpha V alpha. So we've got the rule which transforms V prime into V. It is just eta lambda eta. This is a matrix product. You can just write it eta lambda eta and put the indices mu alpha. Now you can easily convince yourself that eta lambda eta is not the same as lambda. Okay? Because eta changes some signs. It will be the same as lambda with some signs change, but then it's a different matrix. So this is not the same as this transformation. This one transforms with lambda and this one transforms with eta lambda eta. Okay, so that's the difference in transformation between a lower index and upper index vector. And they are two different things. From one you can always get the other. So it's not that one contains more information than the other. You can go back and forth by these two relations. But the transformation under Lorentz transformations is actually different. Now can you see why that didn't happen with rotations? This problem was not there as long as we were doing rotations. Can you guess why?
This time component was not there.
Eta is replaced by 1 in the case, thank you. Eta is replaced by 1 in the case of rotations. 1 lambda 1 is lambda. Lambda was called O. But this 1 on both sides doesn't make any difference. But eta on both sides does make a difference. And in fact, it's a very simple exercise which is done in my notes, that this is lambda transpose inverse mu alpha v. You have to show this from the defining relation that lambda transpose eta lambda is eta. That was how the Lorentz transformations were defined. Using that, you can easily show that the covariant vector transforms as lambda transpose inverse alpha mu, mu alpha v alpha. Okay, and it's the difference between lambda transpose inverse and lambda which makes these two different. But it's also good because we'll see next time that when I take a dot product of this vector with this kind of vector, one lower and one upper, I get a Lorentz invariant. And that's precisely because this thing is lambda transpose inverse. Now I know transpose inverse is a complicated thing to say, but you have to internalize that this is how all covariant objects transform in special relativity. Transpose means we switch the indices. Inverse means it's a matrix inverse. We have to do both. And another way, of course, this is harder because you have to actually invert a matrix. This form of it is easier. Given the matrix lambda, you can easily put eta on both sides, carry out matrix multiplication, and you'll find the same answer because these are equal. Okay, next week, as I posted on the, sorry, I'll stop this video and I'll tell you about next week. So I'm not